Bon.
Everybody, welcome. I'm pleased to introduce you to Francois Rene Rideau, and he is going to discuss security through clarity, why programming, language, and architecture matter. Take it away, Francois.
Hello, so security through clarity. First, we're going to play a game of Spot the Bug. Here is a 17-line smart contract written in Solidity. And before you may spot the bug, I must explain what the contract is meant to be. The contract is meant to let a buyer and a seller close a sale, at the end of which the seller must make a signature or sign a document, and this document may itself release something. It may be a legal document, it may be a transaction on another blockchain, maybe whatever it is. Anyway, the seller needs to sign things, and he won't sign until the buyer gives him the money, but the buyer don't want to give the money until he has the signature. So we're going to do an atomic transaction, a sale, a closing. And in this closing, there may be a bug. There's probably a bug, but maybe you can tell me what the bug is. So the goal is that the buyer deposits the money, and that is only released if the seller signs. It's 17 lines. You think like one of the maybe the simplest possible contract you may write in Solidity. You may or may not be familiar with Solidity, so let's try to go over what this program is and what it does. Solidity 8.2, okay, blah blah blah. This is just boilerplate. There is a buyer and a seller, or both addresses that are payable. That they can send and receive money. There will be a digest. That's the thing we are going to sign. The document, the 32-byte digest of the hash of the document you want to sign. There will be a price, which will be an integer number of tokens, in this case, say Ethereum tokens. We're going to construct the contract as follows. It will take all these parameters here, and you can send money. And the buyer is, we're going to remember who the buyer are and the seller are and the digest is and the price are. We're going to make sure that the buyer who is creating this contract has deposited the value. We could verify that it's a buyer, but in this case, we'll assume that only the buyer is interested in paying and could be very happy. And both the buyer and the seller would be very happy if someone else than the buyer pays, so that no need to verify the identity of the payer. But we verify that the payer does deposit the value into the contract, and then the seller will sign with VRS or the parameter of the signature, whatever. The cryptographic protocol takes these three parameters, and we're going to verify who signed this document and verify that it is indeed the seller. And then we're going to emit this thing that is just a Solidity way to make it easy to recover a signature from the execution. And then we're going to give the money to the sender, who is the seller, because only the seller can sign. So who can see any problem with this contract?
Is message value a UINT?
Message value, yes, it's well typed. It's well typed. Don't worry about typing bugs. There are no typing bugs. How do I scroll? I want to scroll. I can't scroll. Can I scroll less at a time? Maybe with I can do better with what do I call it? The other rival. Here. Is it better here? Here. Yes, it's better. Yay, Chrome. Okay, so can anyone, you don't have to, I mean, this is a relatively specialized thing, and it's fine if no one finds, but let's give you like a few seconds to find. And you can emit random ideas, because I will tell you if your ID is correct. What kind of bug could it be? Okay. And the answer is that it's not easy to find out.
Excuse me, but
yes.
I'm looking at this code.
Yes.
And if maybe I'm missing it, but
No,
it doesn't seem
not.
like message or value are defined anywhere here.
A message is a global implicit in Solidity. It's a message current, it's an implicit of whoever starting the transaction.
So it's assumed I understand that.
Yeah,
even
yeah,
though-
you can assume. You can assume
I don't
it's
know what
well
solidity
typed.
is, so I'm
Oh,
just
sorry.
looking at the
Solidity
code.
is the standard language with which people write smart contracts these days, and it's designed for the Ethereum blockchain. That's what about everyone uses to write smart contracts today. So it is supposed to be a language specialized to write smart contracts. And yet, it's not obvious what this does. And I'm going to tell you two subtle bugs, or not so subtle. The first bug is that the contracts release the money to the sender of the message. And you'd say the sender of message has to be the seller, because who else could sign but the seller? But actually, once you send the message on the blockchain, anyone can see the message. So anyone could see your message that you sign and change the name on the signature on the sender. So the signature here remains valid, but the sender is not valid anymore. And I can scoop your message. So if I see you signing the message, I can race you to the blockchain and get paid instead of you. So that's one bug. It's a subtle bug. It's not easy to understand, but it's there. Another much more easy to understand bug is that, hey, what happens is the seller never signs. That means that the money stayed in the contract forever, and the buyer never gets it back. So you need a timeout mechanism that will ensure that the buyer will get his money back if the seller never sells. And these problems can be solved. So instead of a 17-line program, we could have a 24-line program. But and if you are stupid and you don't do any optimization and you write a straightforward without cleverness, it will take 47 lines. But basically, in 47 lines of code, you could have a correct version of this contract. Now, let's look at the JavaScript client. Can you spot the bug in this JavaScript client for the same contract? So the same contract, and you have the JavaScript client. And I will say to the chase, a bug that there is, this also doesn't do the right thing if the seller never signs. There is no way that the buyer ever gets back his money. So even if you added to the contract, let's say that you fix the contract and you add a missing line to recover, to make the money recoverable, the buyer still doesn't recover his money. Okay, and this is like 17 lines. You see, of course, I have a 20-line also program for the seller. All in all, you have something like between 60 and 120 lines, depending on how good you are, of code to write this thing. And that's a lot of lines in which to hide a bug. Let's see the same application in Glow. And I introduce in Blog. So Glow is a domain-specific language that I'm working on. Let's say this is the same application in Glow. So can you see any bug in it? I'll make it bigger. So that's only 7 lines or 8 lines of code. Can you see a bug in it? So I can go over the thing if you want, because no one knows Glow since it's my language. So let's say where they're going to have a Glow program. It's an interaction. The participant will be a buyer and a seller. There will be some asset at stake, which will be some price. And the contract is called a closing. And it takes a digest as a parameter of type digest. And on the first thing, the buyer will deposit the price into the contract. Then the seller will publicly sign the signature, have a signature, and then we'll withdraw the money and give it to the buyer, and then we'll return the signature. So can anyone find a bug in it?
No timeout.
That would be a bug, except the language automatically does the timeout for you. Good suggestion, great suggestion. And it so happens that the language totally takes care of timeouts for you. So if the seller does not sign, the buyer will get his money back. Great suggestion. Any other bug?
It's assumed that the price is agreed upon here.
Oh yes, of course. This is this is an issue, but it's an issue for all contracts. It is not specific to this or the other or any contract. You always need to agree on the price. Yes, that's a good point, but it's not specific to.
So is it the language or the infrastructure that forces price to be positive?
Both can enforce that the price is positive. Yes.
Oh.
I'm giving you a hint. The bug is on
The
that line.
buyer is getting the money instead of the
The
seller.
seller. Yes. Yes, this is bad. Okay. Okay. Well, it was not. Someone found. I had to help you a bit, but would you say that it was an easier bug to find, or that it was?
Yeah.
Yeah.
It's comprehensible versus the Solidity contract, which is basically incomprehensible.
Yes. And okay, and probably if you were given more time, it would have been better. And but I'd argue you can disagree, but I would argue that it is much easier to find a bug in this 8-line program than in the other program. And here's I fixed that bug in this program. Can you spot a bug in that program? The answer should be no, because I don't think this program has actually a bug. I think it's 7 or 8 lines of code plus 1 blank. I put a blank here to make it clear that there are 2 transactions involved. The transaction then for the buyer. Here the buyer does something. Here the seller does something, and the rest is done automatically. So we have 2 transactions because one thing is done by one party and another thing is done by another party. And the contract then automatically does the thing with the seller. So there are 2 transactions in this contract, in this interaction, and in those 7, 8 lines of code, there is just no space left for much of a bug. And yes, you could put that to the buyer. I know some tools that could find that bug automatically or semi-automatically, although I have not implemented them. But things like if you forget pretty much anything, the language will yell at you. If you don't make the signature public, then you won't be able to return it. Or if you don't match the price, if you forget the deposit or the withdrawal, the language will complain. You can't forget to put the timeout because the language does a timeout for you. This is much simpler. There's just no space to squeeze the bug. And if there is a bug, hopefully the human auditor will have a much easier time to find the bug than in Solidity. So that's the thing I call security for clarity. It's a way to make the program so simple and the language so compressed that it is not even possible to write the bug. And if you do write the bug will either be caught by the compiler or by the human auditor. So the accounts must remain balanced. This is the compiler can do that for you. To make it clear that who is doing what, well, I argue that it's much clearer who is doing what in Glow than in Solidity. You can't public record the signature unless it was made public. So the program will complain. And yes, the program is still valid if you don't return the signature, but then whoever writes the user interface for the buyer will notice. This is a bug that won't go unnoticed. And the language automatically handles timeouts. And yes, also from the same 7 lines of code or 8 lines of code, you get both the smart contract and the client for both participants. So instead of 60 to 120 lines of code, you get only 8 lines of code. That's 90% reduction in the total amount required. That's less time to write the code, less time to introduce bugs, and less time to audit the code. And of course, I'm not saying that just to promote my software. I am here to promote my software, but that's not the thing I want to do. I want to promote a larger point of view about security and software design, which I call security through clarity. And there is a famous quote by Anthony Hoare. I just recently learned that C.A.R. Hoare and Tony Hoare are actually the same person. I thought they were like father and son or uncle and nephew, because so many things by Tony Hoare, so many things by C.A.R. Hoare. No, they are the same person. He wrote that famous thing in his Turing Award lecture and said it too. there are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies. And the other way is to make it so complicated that there are no obvious deficiencies. The first method is far more difficult. It demands the same skill, devotion, insight, and even inspiration as the discovery of the simple physical laws which underlie the complex phenomena of nature. And I argue that this is the security through clarity, and the other is the security through obscurity. And indeed, it can be much harder to achieve security through clarity, but it's well worth it. And it's well worth it because sometimes obscurity is good enough, especially if you can keep modifying your software faster than the enemy. And if a small mistake don't cost you too much, then yes, it's possible to maintain secure software by piling on features and making things complex. But there are some cases where your software cannot afford any single failure, or by the time you discover failure, it's too late. The enemy has already breached your system and got away with the money or the military victory or killed the patient or whatever. So sometimes you just cannot afford the complexity. Only the simplicity and the clarity will make it work. And so, of course, you'll say, how do I make it clear and simple? Yes, you make things as simple as can be, no simpler, but that's easier said than done. Sure, in my 7-8 line program, it's easier than the, say, 100-line program written in Solidity and JavaScript, assuming that the lines are of similar terseness, because line is just a proxy for the actual conceptual complexity. But I'll argue for that in the case of Glow, clearly each line of Glow was simpler than a line of Solidity. So clearly this thing wins. But how do you even achieve that? How could I make Glow so much simpler than Solidity, even though Solidity was also designed to write smart contracts? Do other people deliberately try to make their programs complex? Like, did the Solidity designer, hey, how can we make Solidity so hard to work with? No, they never thought that. They try to make it simpler. And if you compare Solidity of today with Solidity of a few years back, it is slightly simpler or safer. But you don't achieve simplicity just by saying simplicity is a slogan and like, we're going to be simple, repeat after me. No, complexity is a default. Simplicity just doesn't happen by itself. Especially when management says we're going to reward the programmers by the number of lines programmed or the number of bugs closed or the features added, etc. Well, you add, and you never remove. You add in the simplest way for this small add, but not the simplest way overall. In the end, you end up with a pile of steaming junk. And so if you are aiming at simplicity, you have to reward not just adding things, but removing code or averting code to be added and simplifying the software. You cannot just reward adding stuff to the software. And you also need to understand where the simplicity comes from. And that's where it comes from is abstraction. So abstraction is when your language takes care of a lot of details, so you don't have to. And abstraction supposes two levels of abstraction. An abstract level, which is typically pictured above. I don't think these slides help. Should I remove the slides or should I keep them? You tell me. And a concrete level of computing, which is usually presented below. And you have a relationship between the two. And usually the concrete level is given to you from the hardware you have, from the operating system you're using, from the environment in which you're running and the other computers in the universe, and from the system programming language you're using. And all this gives you a concrete level to build on. But what you want is actually a more abstract level, a level that is sufficiently low level. You want the abstract level to be low level enough that you can express all the concepts that matter to you. If the only thing you can say is do what I mean, that's the ultimate high level language, it's not useful because it doesn't, unless the computer can read your mind, it cannot tell exactly what it is you mean. So you have to have low level enough that you can tell what you mean. But it should be high level enough that it will shield you from all those details that don't matter to you or shouldn't matter to you because they could be automated, but they aren't. So abstraction depends on this relationship between an abstract level and a concrete level of computing. And it's not a novel thing. It's not even something that people deny or don't use. People always use abstraction in the choice of their programming languages. No one today writes software directly in binary, like people used to do in the 40s or 50s. No one uses assembly language anymore. Very few people use assembly language as they used to do always in the 50s and 60s. There were like assembly language was replaced by Fortran and COBOL, and there's been replaced since by C and C++, Java, Python, JavaScript, Haskell. There are like tens and tens of languages that people use. And there's no clear winner for one of these languages is better than the others in all ways, but they all tend to abstract over a lot of the details that people don't care about, while letting people express those concepts they do care about. So people do choose their language based on power of abstraction. And even now, in the Linux kernel, you have seen that C is being replaced by Rust. That happened at the margins of the kernel, like device drivers, but now you can write your device driver in Rust because Rust eliminates a lot of catastrophic memory leaks and buffer overflows that you have in C and C++. And that's a big deal for security. But even these general purpose languages offer you only a few rigid abstractions. They are general purpose, that is, they are not tailored to your problem. You can abstract over few common issues, such as memory safety that Rust tackles, and that Lisp and other dynamic language tackle. But there are plenty of things that it doesn't have. So let's go back to my smart contract language. Solidity and JavaScript are general purpose enough that they could not make the concepts such as making the participant payments obvious solved. They couldn't solve the keeping accounts balance problem for me. They couldn't solve the handling timeout systematically problem for me, or the keeping the participant software in sync with a smart contract problem. And all these are things that could be automated, but are not, and obviously cannot be in a general enough programming language. They can only be automated because what I'm doing is specific and more restricted. And I don't know what domain you are working on, each of you, or but whichever it is, and with whatever programming, general purpose programming language you use, is missing a whole lot of the concepts that you need for your problem at hand. And the problem is that, another problem is that these languages allow you to write libraries. Oh, you want a new concept, you write, there's a library for that. But these library abstractions are leaky. That is, they do only half of the job of a proper abstraction. What are the jobs of a proper abstraction? Two things. One, it must translate from the higher abstract level to the lower concrete level. And usually with a library, you can kind of do that. It's just a bit of handwork involved, but yes, the library will translate a lot of the high level concept into the low level concepts. However, what it does not do, a library usually, is hide the details of the concrete level and make them inaccessible, which means that these concepts will creep in your program. The abstraction will leak. It will have to be messed up with lots of details that comes from the side and everywhere, and you have to deal with them by hand. And so the abstraction is leaky, and it doesn't protect you from all these problems. It just say, if you use it correctly, that's right, but nothing helps you do it correctly. So a good abstraction would do both the translating from the high level to the low level and the protecting you from the low level. So we would say that the abstraction is airtight, and the programming language researchers would say that it's a full abstraction. But the same thing means it's not leaky. You don't have to deal with the details anymore. They're dealt with for you once and for all. So when you don't have, when you have leaky abstraction, when you don't have this hiding the low level details, you add discipline. what is discipline means like, okay, if I follow the rules, if I do the job that the compiler will not do for me, if I audit the code systematically, if every time I make a change, I make sure the change is propagated each and everywhere it needs to be propagated to, etc. If I compile my design patterns by hand, if I follow the protocol to the letter, if I'm myself a perfect machine, I can maintain the iron discipline and make it work. Unhappily, you are not perfect. Your discipline will be tired someday. Someone else in your team will be tired, or there will be a newbie who doesn't understand exactly all the places that the changes have to be propagated to. Sooner or later, especially as the program grows and grows and grows and grows, because you never reward simplifying, sooner or later there will be a catastrophe and big leak, and the security will go to the toilet. Discipline is costly. Perfect discipline is infinite costly. And so the gains you get from the leaky abstraction are sooner or later overcome by the cost of maintaining the leaky abstraction. What can improve those odds? Type abstraction, for instance. Some modern programming languages, especially the more modern ones, such as Haskell or Scala, have expressive type systems that allow the library implementer to also express constraints on how to use a library in those types. And then the language makes it impossible to misuse the library in a way that violates the types. And sometimes that is enough to make your abstractions airtight. Oh, if you use those types, there's just no way possible to abuse those types. And sometimes the abstraction is still leaky, or there's no types, but the types only express like some properties of your abstraction. There are other properties that you still need to manually enforce. So they call that laws of your abstractions. Your monads have laws, your library, whatever, has laws, and you must follow the laws. But at least the type system can help you somewhat. And in some cases, that helps you enough that auditing become much easier. So it's like having a boat that have a few leaks. You still must constantly bail out the boat, but at least it's doable. It's better than having a wreck that is more holes than hull, and in which like it doesn't even float. So sometimes that's enough. But what do we want if we want a real full abstraction? If we want a real full abstraction, we need what we call language abstraction. Language abstraction is where you build a language, and this language allows you to say exactly what you want and nothing else, and therefore everything you say has a meaning, can be translated, can be processed automatically, and you may want to restrict what you can say so that the compiler can automatically process what is said. And since we're in a security audience, this is very close to the concept of language theoretical security. Who here has heard of LangSec? Language theoretical security.
I have.
Zoe, congratulations, Zoe.
Yeah, it's one of my
Okay.
favorites.
Okay.
Me
so
too. Have we ever brought
LangSec-
Meredith Patterson to speak here?
Oh yeah, I would love to hear
I
her.
want that. Her Falcon Dark Star. I want to try to get type to speakers in the future.
Yes.
If anyone has a direct connection, please hit me up.
Yes. Okay. You can. I know Meredith. You can send me a. Yes. Okay. Send me. Send me.
Awesome.
Yeah. I can forward the invite. So
Great.
LangSec, promoted notably by Meredith Patterson and her friends and former. Let's not go over personal details. But it's the idea that every I/O is a language. Your program's I/O constitutes a language, like the user inputs something and gets something in return. Any user interaction, you move the mouse, etc. It's kind of a language. Every program, therefore, is a language to its users. Every program is a programming language from the point of view of the users of the program. And if somehow the more powerful that language is, the more the user controls the program, and the more the potential adversary may control your program. So if you have a program on the internet, if it's a local program and you give total control to the user, no problem. But if it's a program on the internet and it gives total control to the adversary, that's bad. So, and if your language is a Turing equivalent, the language you offer to the people on the other side of the internet, then you're pwned. Your computer is pwned. The adversary can make you do whatever he wants. So there's a whole cool school of LangSec that recognizes, yes, every program is a programming language, and you should think in that term. But instead of thinking in that term only in a deconstructive ways, oh, we have to analyze a program that way, we can also use this approach to build software better, where, oh, but it's not just in a negative way that every program is a programming language, it's in a positive way. We can make every one of your programming language and adapt that programming language to the task at hand so that every program can be written in the ideal programming language for that program. Oh, you are doing finance, let's design the programming language for financial transactions. Or you are doing data science, let's write the programming language that's perfect for data science. You're doing whatever you're doing, and maybe there's something more specialized than just general purpose data science. Maybe you're doing some special kind of networks, like neural networks, or you're doing some special kind of whatever it is. Well, let's build the language for whatever it is and you always write a program in the ideal programming language for that program. That's the domain-specific language school of thought. There are people who do that everywhere, but there are languages such as Force, Lisp, APL, Scheme, and Racket that emphasize this school of thought and of approach of programming language. And especially Racket is the one that takes it the most seriously, where you don't build just one domain-specific language. You build towers of programming languages and modules of that implement part of a programming language. And that's where you can build abstractions on top of abstractions. Instead of building directly the language, the ideal program language for me, I will build my ideal language on top of the ideal language to build the ideal language, etc., etc. And sometimes some of your abstractions leak, but even then, as long as the overall building doesn't leak, it's much easier to maintain the discipline you need to deal with those leaky abstraction when the overall construct itself is something that does not leak. So there is no external source of leakage that will seep into your lower abstractions. So this approach of building your program in terms of languages is very powerful. And to a point, it can be also combined with types, etc., where we haven't found yet the perfect solution that deals with types and languages and metaprogramming. It's still under development, but it will give you so much more mileage than writing things in C or in assembly. If you really believe that abstraction did not matter, you would be writing in assembly for the performance, wouldn't you? And so taking action. Of course, you can't transform today all your program into something written the right way, whatever the right way is, even if your right way disagrees with mine. But you can choose your language strategically. What language did you use yesterday? What will you use today? What will you use tomorrow? Obviously, these questions do not have to have the same answer. Yesterday I was using C because it made sense. Today I'm going to use Python because it makes sense. Tomorrow I went, hey, what am I going to use tomorrow? Well, it depends. If I need something done like for tomorrow and it will be thrown away next week, I will use whatever language is at hand. Like right now I'm using, say, Scheme, I use Scheme. You are using Python, use Python. You're using assembly, use assembly. That's the language you have at hand. But if you are doing something that's more like a year of horizon, maybe you should use a popular tool. There's a reason why this language is popular. Oh, in machine learning, they use Python, let's use Python. Or use R, whatever they use. Use a language that is popular because it makes sense. It's whatever is good today. It's a project with a 10-year horizon. Now that's where you need to really think strategically. What is the language that from now to 10 years from now will minimize the pain, will allow me to have the best abstractions that don't leak and build those abstractions when they don't exist yet. And then there's 10 years, there's 20 years, 30 years, etc. What is a language that still exists after 50 years? Well, there's COBOL. COBOL is 60 years old if you want to use it. And that's Lisp. Lisp is 60 years old, and I think that Lisp will still exist in 60 years in a way that COBOL won't. Anyway, you don't have to agree with my opinions, but you better take seriously the fact that there's a strategic choice to be made there. And to get there, you don't have to migrate your entire code base at once. You can do it incrementally. There's this post by, I think this Android team or whatever, was explained how in Android they take the approach of, hey, what are the parts of the system that most need to be translated in a safe language? And they use the safer tools there. So you don't have to transform all your system to already enjoy today the benefits of better abstractions and better abstractions to language abstraction when it's possible. And I will conclude by saying that clarity is more than for security of computer systems. It's also security of your own head. If you accept any explanation that is more complex than it should be, it means that you are letting someone else insert information in your operating system. And if any times you accept a leaky abstraction, or you accept an abstraction that is too complex, you're being manipulated. And if you do that as a matter of course, you're being systematically manipulated. There is a philosopher who discussed the notion of reduction ad claritatem, reduction to clarity. I think it's very important. And I'll finish that there. And I'll finish on the Hoare quote. So that's I think that's the best page on which to finish the talk. Thank you for listening. And I hope you enjoyed this talk.